Today, we're going to connect two totally different worlds, a brilliant military tactic from the 1700s and a powerful mathematical law cooked up during World War I. It's an incredible story of how a general's gut feeling on the battlefield was eventually proven with absolute certainty by an equation.
So let's start with the central puzzle, the big question. How can a smaller army, time and time again, just crush a much larger one? I mean, it goes against everything we think we know, right? More soldiers should equal more power. But history is just littered with examples where that's, well, it's just not true. So what's the secret? How is that possible?
Well, a big piece of the answer lies with this guy, Frederick the Great of Prussia. He was almost always outnumbered, yet he pulled off some of the most jaw-dropping victories of his entire era. Now, his secret wasn't some new super cannon or a better rifle. It was an idea, a whole new way of looking at the battlefield itself.
And that brings us to our first part, the Prussian paradox. We're going to look at how Frederick turned having fewer soldiers into his greatest weapon.
This was his secret weapon. It was called the oblique order. And honestly, the idea is so simple, it's brilliant. Instead of spreading your army out evenly, line to line, you do the opposite. You intentionally make one part of your line weak so you can pile the rest of your forces onto one single point of the enemy's line, usually their side, their flank. You're not trying to fight their whole army at once. Nope. You're creating a tiny local battle that you know you can't lose.
Let's break this down, because it's like a kind of deadly dance. First, you basically tell one of your flanks to just hang back. Just hold the line, nothing fancy. Meanwhile, your other flank, your strong flank, marches forward in this weird angled staggered formation. Their job to just smash into the enemy. Once that enemy flank breaks, and it will, you just pivot your whole army and roll up their now chaotic line from the side. It's beautiful and it's brutal.
This quote just nails it. It's not about having more soldiers in total. It's about having more soldiers right there, at the most important point, at the most important time. That's how a smaller army gets what they call local superiority.
But, and this is a huge but, pulling this off was insanely difficult. It took an army that was just on another level. First, you needed absolute iron-willed discipline to march and wheel around while people are shooting at you. Second, you needed speed, which Frederick got by reintroducing cadenced marching, having soldiers march in step, something nobody had really done since the Roman legions. And third, you needed incredible cavalry to guard your exposed side. This was a true high-risk, high-reward strategy.
And the payoff? Oh, it was huge. Just look at the Battle of Rossbach. Frederick's tiny Prussian army used a perfect oblique order to completely shatter a much larger French and Allied force. It was an absolute masterpiece. But for over 150 years, everyone just saw it as military genius, as art, not as science.
Well, that all changed in World War I. Which brings us to Lanchester's square law, the moment where battlefield intuition finally got its mathematical proof.
Now, let's just put this into perspective for a second. The basic idea of concentrating your force, it's ancient. The Thebans used a version of it to beat the Spartans way back in 371 BC. Frederick the Great basically perfected it in the 1700s. But it wasn't until 1916 that an English engineer, of all people, named F.W. Lanchester, finally explained why it worked using math.
So, Lanchester came up with two models. The first one described ancient combat, swords and shields. Casualties are pretty much one for one. But his second model, the one for aimed fire from modern rifles, well, that's where everything changes.
This is it, Lanchester's square law. It says that in a modern firefight, the combat power of your army isn't just based on how many soldiers you have. It's based on the square of that number. And that, right there, is the game changer. It means that having more soldiers gives you an advantage that isn't just a little bigger, it's exponentially bigger.
And this table just shows it perfectly. Look at this. If you go from having 5 soldiers to 10 soldiers, you haven't just doubled your combat power. No way. You've quadrupled it. It jumps from a power of 25 all the way to 100. A small difference in numbers creates this massive, overwhelming advantage in firepower.
So, here's the aha moment. Lanchester's square law is the math behind Frederick the Great's genius. When Frederick concentrated his troops, he wasn't just adding more soldiers to one spot. Unknowingly, he was multiplying his combat power. By creating, say, a 2-to-1 advantage in numbers on that flank, he was actually creating a 4-to-1 advantage in fighting strength. He was bringing a cannon to a knife fight.
Okay, so that's all fascinating history, but how does this stuff apply today?
Well, Lanchester's work was just the beginning. It's the foundation for all modern combat models, which have to deal with way more complicated situations.
Exactly. I mean, real war is messy, right? It's not always just a clean two-sided fight. You've got alliances, you've got chaotic battles where multiple factions are involved. How on earth can math even begin to model that kind of chaos?
Well, the answer is a really clever tool called a conflict matrix. You could think of it like a spreadsheet for war. It just tells the equations who is fighting whom at any given moment. And using this, we can start to model battles with 3, 4, 5, or even more sides.
So let's look at a scenario, a total free-for-all. Everyone is fighting everyone else. In this situation, the math is absolutely ruthless. The model predicts that only one army will be left standing. And the winner? It's always the army that starts out with the highest combat power, which is basically a score that combines their skill and their sheer numbers.
Okay, but what if you team up? In this scenario, you've got a bunch of armies forming an alliance to take down one big common enemy. Here, the outcome is just a straight-up comparison of power. If the big single army's combat power is greater than the combined power of all the allies, it wins. But if the allies have more combined power, they win. And what's really interesting is the model says they all survive, even the little guys in the alliance.
What's so incredible about this is that it shows that even in the total chaos of war, there are these fundamental mathematical rules at play. The math can actually cut through all the noise, and if you know the starting conditions, it can predict the most likely winner with stunning accuracy.
So let's bring it all home in our final section, the mathematics of victory.
We started this whole thing with Frederick the Great, a military genius who just knew, in his gut, the incredible power you could get from concentrating your forces.
And we end here with Frederick Lanchester, an engineer who, more than a century later, took that gut feeling and translated it into the pure, universal language of mathematics, giving us the elegant and powerful square law.
Which leaves us with one last, really fascinating question to think about. If the outcome of a battle can be predicted by a set of equations, what is the true role of a general? Is their art just to manipulate the starting numbers to create the best possible conditions for the math to then play itself out? It's a pretty deep thought to end on.